Today we're very happy to welcome Maxim Kontsevich, and the title is Quantum Minimal Surfaces and Kaehler Non-Commutative Geometry. Maxim,
okay, thank you. Yeah, let's start to share screen, suppose. Yeah, just a second. Yeah, okay. So you see, maybe a little yourself. Yeah, okay. So this is talk which, in fact, I gave a essentially identical talk a bit more than months ago, but in Russian, so not everybody was able to follow. Yeah, so it's based on two papers, one with Joachim Arndt and Jens Hoppe on quantum minimal surfaces, and another with Gaurav Bhattacharya on Kaehler non-commutative geometry, and the subjects are closely related. Okay, so oops. Okay. So there was, in the very early days of string theory, there was something called, physicists invented, oops, sorry, my computer's a bit overloaded. Okay. Maybe I just do full screen, just a second.
Yeah, maybe full screen would work better.
Yeah, okay.
You would see the full slide.
Yeah, but then it's your little, you will be little, okay, maybe it will be no little you. Yeah, so there was action functional, one of possible action function for strings, written in the following form. We map a surface with symplectic structure, not metric, but symplectic structure to Riemannian manifold. And the action is defined in the following way. You consider a corresponding map from wedge square of tangent bundle to wedge square of x. In wedge square of tangent bundle, you have inverse to symplectic form, Poisson structure, you get some element, you take map it to wedge square tangent spaces, because Riemannian have some L2 norm, it takes square of the guy, you get some function, and then multiply by volume element on the surface and integrate. Yeah, if you don't raise to the power 2, but raise to power 1, you get just area of the surface with respect to induced metric. So it doesn't really depend on choice of symplectic structure. But if you raise to power 2 or any other power not equal to 1, you get something which depends on symplectic structure. And like for particles, you can consider length of particles of integral square derivatives. It gives essentially the same thing. Here's a similar story. If you can consider critical points, solution of Euler-Lagrange equation, you get essentially minimal surfaces. It's a kind of nice class of solution. You get embedding of your surface or local immersion of your surface to your target space, maybe outside of few critical points. You get a minimal surface, and the volume element is proportional to volume element with respect to induced metric. So if you have some kind of like isolated minimal surface, you get still infinitely many maps because you just add by symplectomorphism of the surface. And the action for non-degenerate solution will be strictly positive. But there are stupid degenerate solutions, namely, you just map your surface to a curve arbitrary way, and then embed this curve again arbitrary way to your manifold. And then this thing will be 0, and the action will be 0, definitely critical point because it's non-negative, and 0 it's minimal point, critical point, or you can even map to a point. So it will be a huge variety of very degenerate maps, which you shouldn't consider the minimal surface at all. There's no minimality. This curve could be arbitrarily long and so on. Now, if my target space is Euclidean space, the map is just a bunch of functions, a real valued function on my surface, and the action is very easy to calculate. It's integral of sum over squares of Poisson brackets of these functions. And I forgot to put omega here. Okay, and if you want to consider what is Euler-Lagrange equation, variation derivative is 0, you get this nice looking equation. It's clear, you get this something of degree 4. Now you get derivatives get something of degree 3. So the sum of double derivatives for each variables is equal to 0. So that's first story. Okay, so this shield action, I just write it again. You see that omega appears 2 times as a something for integration and ends it for Poisson bracket, but we raise it square, so that homogeneity degree -1 in omega. So if you multiply by lambda, the section will be divided by lambda. And just to cancel this homogeneity, we multiply by something which doesn't really depend on the choice of embedding, by multiply by area, and the normalized shield action will be invariant under rescaling. Only by constant. If you replace constant by function, it will definitely not invariant. So it's no longer local functional, it's product of two local functionals in the sense, or this product of two integrals. And the critical values of the things are now take discrete values because this rescaling play no role. It will be still 0 for trivial solutions and squares of areas of non-trivial minimal surfaces. So you get, in general, if the target is compact, not like Rn, and then you should get countable set of critical values. So now the next goal, define something like quantum analog of this normalized shield action, and it goes through the following dictionary. So it's quantization. Sorry, this may think shields a little bit the title. So what is quantization? You start with a compact symplectic manifold of certain dimension 2D, and let h bar will be Planck constant, which will be not a constant but a parameter which tends to 0. It could be in fact in what follows it will be something like 1 over integer. It's not a continuous parameter, and when the manifold is compact, and then the quantization, it's not canonical procedure, but it's some kind of association, class of associations. That for small h bar, we have certain finite dimensional Hilbert space, which depends on h bar. I will skip h bar from notations. And dimension, when h bar grows tends to 0, it will grow some 1 over 2 pi h bar to power d times this symplectic volume, and 1 plus small over h bar. When you get a function on your manifold, real valued function, so equal to its complex conjugate, then for small h bar should have a self-adjoint operator acting on the space. And the main rule is that it's quantization of a function, and the main rule is that the product of quantized operators is operator for quantum product plus IH bar over 2 quantization of Poisson bracket plus higher order terms. One can ask that, for example, this should be form power series in h bar, have a symplectic expansion in h bar, and it will be star product. So usually people say about real value functions, self-adjoint operations, but one also can add into axiomatics that if you have a function is values in a unit circle, then it should give rise to unitary operator. And if it's exponent of actual I times real function, it will be exponent of this self-adjoint operator. And the rules are essentially the same. The product of heads of unitary operators is corresponding to functions. It's interpreted of the product by exponent. And here wrote some kind of funny expression. I take Poisson bracket u1, u2 divided by u1, u2, which is locally Poisson bracket of logarithms. Globally, logarithms are not well defined, but Poisson bracket is well defined, because logarithms are defined up to a constant. So you get these things, multiply, quantize it, multiply by HR2 plus add some higher order terms. That will be correction to the product. Okay, then we can integrate functions of a manifold with respect to symplectic structure. For example, if we take 1, we get volume, and then it should correspond to a trace of operator plus higher order terms. Oh, actually, I was wrong. Of h bar to d minus 1. So there's a misprint here. And just a second. Oh, maybe no misprint. Yeah, sorry. It's number of size 1 on the left-hand side, so it should be 1 plus small of H bar. Yeah, so the things should be like for function 1, the quantization identity operator, you get this formula for the dimension. Yeah, and just in case when dimension is manifold 1 and manifold surface, then you just integrate form function with respect to omega, like we do in shield action. Yeah, and just I repeat this Poisson bracket, it goes to 1 over H bar bracket of operators. Okay. Okay, so this was our shield action. This is a dictionary how go from symplectic geometry to quantum mathematics. But before going on, I just want to show you this basic example of quantization. Our manifold is a torus, product of 2 unit circles, and the symplectic form is 1 over 2 pi d theta1 times d theta 2. So the integral formula is 2 pi. And then H bar will be 1 over integer. Hilbert space will be C2Rn. This will be some pretty canonical thing here. So in this case, it's really convenient to use not self-adjoint operators, but unitary operators, because on the circles, we have natural functions with values on circle, just first 2 coordinates on the torus, exponent of I theta1, I theta 2. And the corresponding operators will be operators in dimensional vector space, just cyclic permutations of base elements and multiplication by the diagonal matrix. Okay. Then, yeah, so in this example, you see that product of U1, U2, it's equal essentially. In U2, U1, you see these formulas for commutations for unitary operators. So what will be general construction of quantization? So I assume that omega has homology class, which is 2 pi times integer class. So it's first chain class of some line bundle. So I get some this line bundle with unitary connection is curvature form I omega. And then I choose arbitrary almost complex structure on manifold compatible with omega. Then for H bar in 1 over integer, when n is sufficiently large, I define this Hilbert space as a kernel of Dirac operator, I want to say. So I consider sections of my big power of my line bundles multiplied by d bar forms. And then to take, using this connection, I have notion of d bar derivative. It's d bar square will be no longer equal to 0, but still first order operator. I take a Hermitian adjoint operator, take d bar plus d bar prime, consider operators from even to odd part. It will be some kind of Dirac operator. Why I take kernel? Because for large n, the kernel will be 0. So I get this for large n, I get some finite dimensional space whose dimension is calculated by index theorem. And the operator corresponding to a function is given by the following. What is it? Some misspring, some scrunk here. It's M. Not what is K doing here? It's some typos. Sorry. It's defined as a composition. I consider this finite dimensional subspace of this harmonic spinors, kernel of the Dirac operator, embed the space of all sections multiplied by function, and then because it's some Hilbert space, take a back orthogonal projection. Okay. So I hope you are with me. I don't hear anything. Hello?
Oh, that's because we mute our micros. Otherwise, it would be too noisy. Yeah,
okay, yeah, but you are with me because I cannot see. I just make it see very small. Oh,
yeah,
maybe
no, don't worry. When we don't understand something, we ask you.
Okay, yeah, at least I'll see maybe small your. Okay. Okay. So we have this normalized field functional. So in this case, symplectic manifold is 2-dimensional. And then I denote by capital N the dimension of this Hilbert space. And I kind of informally write like I map my space to Rn, not to some compact target, but to Rn. So the map to Rn was given by a bunch of real valued function, and in quantization it corresponds just bunch of self-adjoint operators. And now I look for this expression for normalized shield functional. It's product of two integrals. And according to the dictionary, I replace this first integral by dimension, trace identity operators, n times 2 pi h bar. And second by also replaced by rules by another trace, also multiplied by 2 pi h bar. And if you look here what's going on, you multiply, you get h bar, and my h bar in the denominator, h bar disappears, and you get 2 pi square n times trace of sum of squares of commutators, take minus sign because I, it's still positive number. Yeah, so it will be an analog of normalized shield functional. So we don't have to speak about h bar because it's normalized. And the earlier Lagrange equation for this function is very similar to what I wrote in a classical station at the sum of double commutators is equal to 0. In classical stations with Poisson brackets instead of commutators. Yeah, so it's all very nice. We have equation of motions, we have function functional, but there is a little problem. In Rn, there's no compact minimal surfaces. Yeah, so there are various ways to deal with this problem. Yeah, for example, one of way it's just impose some constraint. My surface is should lie on some things given by a certain equation or several equations, for example, on a sphere. And you just naively, for example, if you write a sphere, take sum of squares of variables equal to 1, you replace by operator identity sum of squares of n by n self-adjoint operators equal to identity matrices. Yeah, so it's it looks nice, but it's not really well defined. And there are a lot of ambiguity here. So, for example, this suppose my I wrote some equation, but not of second order, but fourth order, for example, yeah, some fourth order polynomial in xi. And when I get when I want to apply to this matrices capital Xi, I have some ambiguity. I can, because matrices are not commuting, I can put in one order, another order. Still, I want to have expression to be self-adjoint. But there are many ways to do it, and so it's not really canonical procedure. But I don't think it's really relevant in the story. Oh, it's somebody's kid, yeah.
Yeah, maybe I think everybody should mute, right? Yeah, otherwise it might be too noisy. Nikita, could you look into it? Yeah, sorry.
Yeah, so it's not terribly canonical procedure, but it's at least something. Then you can put this constraint, and when you write Euler Lagrange equation, what you do, you put Lagrange multipliers. You know, if you had put certain constraints, you add to your function linear combination of constraints with unknown vectors and solve the equations. Yeah, so that's one way. Another way, it's kind of, if you want like nicer formulas, you just want, instead of mapping to Rn, you want to map to torus. You consider U1 to power n, and but put here some constant flat metric, not just product of circles, but given by some small n by n symmetric real positive different metrics. So, so the rules of the game is the following: we have map from symplectic surface to U1 to power n will be n functions is absolute value equal to 1. You translate by dictionary, you get n unitary operators, small n unitary operators of size capital N by capital N. And when you write quantum action, just one of possibilities, again, it's not terribly canonical, is the following. First, we get this capital N as a factor to make normalization shield functional, and then take some of a like squares of Poisson brackets. So I get 2 by 2 minor so my symmetric metrics. and multiply by something which is written here. I take 2 times identity matrix and remove 2 group commutators. It's something very close to 1, and if this commutator is exponent of I small number, it will be something like cosine of this number. It will be something like square of this number. So it's replacement of the square when the 2 operators almost commute. Yeah, so it's again kind of ad hoc formula. Maybe there are better ways to do it. And one can make a kind of analytic conjecture, and there's very, very freedom in this conjecture. Like when you put constraints, so you replace in the second case by something similar. That when you take critical values of quantum shield action, which is product through traces, each one is dimension, on a solution of Euler-Lagrange equation which are indecomposable. I think it's really kind of crucial story here, because when you consider the Euler-Lagrange equation, you can make direct sum of 2 solutions, block direct sum, and it's behave kind of bad because the action is not local. You multiply just 1 trace, but you multiply by dimension, so you can make kind of complete mess from these direct sums. So one should look only on the indecomposable solutions, which are not direct sum of 2 simple solutions. And the conjecture that on such kind of decomposable things, the limit when dimension goes to infinity goes to this nice countable set which appears in a classical situation, which will non-degenerate critical values of the normalized shield action, which is always a countable set, which are squares of areas of minimal surfaces. And here you see that you get a lot of possibilities, because first you can choose any submanifold in Euclidean space by given by any collection of equations, any compact submanifold. There are very many these manifolds, functional freedom, or even in flat case, you get also many things. Yeah, in principle, you can do some computer experiments with this and try to see what is going on. So we have.
Maxim, I have a short question.
Yeah?
So many years ago, I think in physics, they were looking at that equation that you have now, this Euler-Lagrange equation, and it was called some kind of matrix M theory or whatever it is. So
yes, it's actually ubiquitous in string theory, this equation.
Yeah, so
matrix models, yeah.
Right. How is it related, right? You also want to find some classical geometry in that equation. I don't quite remember what they were getting, but basically they were saying that all the structure of the universe is contained in that equation.
Yes. Yeah, there was this Japanese model. It's also some kind of Banks equations. Yeah, there was. Physicists know very well this stuff. Yeah, it's just lecture for mathematicians. Yeah. Okay. Oh, sorry. Go down. Yeah. Now there's actually some side remark which will be returned at some point, that if you have a map from, in general, have a map from surface to some remaining manifold, this map defines homotopy class, in particular homology class, and H2 of your manifold. And then one can try to minimize area in a given homology class. And when the target is scalar, then there is a a priori low bound. This, if you have any surface in a given homology class, then this area is bounded below by the integral of, because it could be positive, negative number of Kaehler form of your surface, which depends on the homology class. Because of pointwise inequality, just pointwise, for any small kind of piece of tangent space, you get this inequality. The integral of two form will be low bound of area element. And it's called calibrated geometry, and the inequality became equality if and only if this curve is holomorphic. And this is this calibrated geometry business. This pointwise condition. So one can ask as a question for this quantum maps, can one have this inequality? And first one have to speak what is homology class of a surface. And there are two examples which I worked out. One is the following. Suppose my target is n-dimensional torus. It's some flat metric, but for metric I don't care, just a question about topology. And my quantum map is just collection of n unitary matrices of very large size. What will be homology class? The homology class is element on the lattice of rank n-1, n-2, so the components of this homology class ij for each I less than j, for each pair of indices. And when you try to write formula in classical geometry, what you do? You take Poisson bracket of the thing and multiply by symplectic form and integrate over surface and divide by 2 pi squared. This gives you exactly the degree of a map to two-dimensional torus. And so it's not a shield function, it's something literally invariant under rescaling of omega. You don't have to multiply by area. And according to the dictionary, you should replace by trace. And then the claim that this trace is really close to the integer if your operators are sufficiently close to commuting one. If kind of operator norm of commutant commutator is less than constant over n. Like for the standard example which I started from the beginning of a torus, when you get this rotation and multiplication by exponent, the commutator was of size 1 over n. But if you consider any two operators with this bound c and capital N goes to infinity, and I calculate this trace, I claim it will be very close to the integer which is less than c, absolute value. So I'll give you as an exercise. It's a very simple exercise. And another example is when the target is sphere. So in R3, I write equation, sum of squares of 3 variables is equal to 1. And degree of the map, if you get this standard kind of like area element on the sphere, it's given by this integral. I just consider this map from identical map from sphere to itself should be 1, and then you get exactly this thing. And now there's a bit non-trivial lemma. If you have 3 self-adjoint operators, or again misprint x2 should be also raised to power 2. I'll correct my slides. Is equal to identity map. Then this and if commutators again satisfy the same inequality, with constants is fixed and capital N also very large and operator self-adjoint, then the claim that if you replace this expression by this thing, you get again something very close to an integer. The error will be of something constant over n, and this integer will be less than something like 3 times c. Okay, so there is notion of degree map, but also let's return to non-commutative, non-compact case for a moment. So non-compact case, we cannot speak about degree and can speak about normalized shield functional, but it's a really nice piece of mathematics, classical geometry, because if you consider Miller surfaces of some kind of finite type, after translation, it's essentially object of algebraic geometry. Namely, if we had non-compact surface, which is embedded as minimal surface Theorem, then one can, I don't speak about symplectic structure surface at all now. Then on surface you get one forms, dxi, and we have induced, remaining metric induced conformal structure. So it will be actually complex curve. And assume that this complex curve is kind of finite type, algebraic curve minus finitely many punctures. Then what happens that each one form, d of coordinates, will be real part of holomorphic one form. It will be harmonic form. Xi will be harmonic function on the surface. and then reduce to the following equation. You get n holomorphic one forms, so that all periods of this form are pure imaginary, so real parts of this form will be differentials of global functional surface. It's some equation on periods. And then another equation, which is a pointwise equation. If you take each sum of squares of this holomorphic conform as quadratic differential, then it vanishes. So it's very easy to produce, like, for example, this curve with just affine line C, it produced 3 functions, 3 polynomials with sum squares equal to 0. Very easy to solve these equations. And multiply by dz, and you get the solution of this equation. So it gives some kind of called n per surface. Yeah, so it's essentially equation of algebraic geometry. And in the compact case, now I jump back to compact case. If you consider minimal surface and flat torus, it's more or less the same, because locally the picture is like this. So you get curve with if you consider, it's actually very nice. You get complex curve, no punctures, a bunch of holomorphic one forms. Sum of the squares of forms is 0. But then imaginary parts of periods of this form should satisfy some line, will be some given numbers depending on shape of your torus and homology class of your surface. And then you get this description in terms of algebraic geometry, what is going on. Yeah, so it's actually still a puzzle for me. All this language, I have really no idea how to translate to this quantization business. It's still open question. This Weierstrass parametrization, how to translate to this language of self-adjoint operators, I have really no idea. Yeah, but okay, now let's jump back to non-compact Rn things. So we get this map to Rn, which is described by some kind of nice algebraic geometry. And if you try to see what will be quantization, definitely the Hilbert space will be infinite dimension because the surface has infinite area. It should be roughly some holomorphic functional section of canonical bundle on the curve. And Euler-Lagrange equation says that you get some Hilbert space completion, and consider a bunch of self-adjoint operators in the space satisfying this equation. And this should probably have some common domain of definition, but nothing is clear here. And what are boundary conditions infinity, it's also not clear. Yeah. So now I go to this calibrated geometry, which I mentioned before, which is actually some particular case of what is called supersymmetry in classical field theory. So usually when you consider Euler-Lagrange equations, it's some kind of energy or mass, and equations are typically of second order. The symbol is Laplacian, so you replace some kind of harmonicity. And supersymmetry says that there are equations of first order, and number of equations could be different, but some collection of equations of first order which are in a sense much simpler, which implies the equation of second order. And explanation, it's some general BPS inequality, like area is bounded below by absolute value of integral of some topological invariant, and in general certain mass is greater or equal to mass of absolute value of certain topological charge. So there are two basic examples which everybody knows. So consider Kaehler manifold and consider complex submanifold of any dimension. The complex submanifold, it's a manifold, it's a real submanifold satisfying first order equations. So on the tangent space, you get Cauchy-Riemann equation, should be holomorphic pointwise, and they're automatically minimal, which is second order equation. Now that's literally calibrated geometry, and if you consider manifolds of dimension, complex dimension 1 will be this minimal surfaces given by complex curves. And another situation is similar, but now consider bundles on manifold, and consider Kaehler manifold, and consider first holomorphic vector bundles. Holomorphic vector bundles, first order equation on a connection, like curvature in d-bar direction vanishes. And now endowed with Hermitian norm satisfying Hermitian Yang-Mills equation, which is again some first order equation on connection. And these things again satisfies inequality and give solution of the usual Yang-Mills equation, which is second order equation of connection. So people are familiar with this in complex dimension 2 and real dimension 4, but it works in any complex dimension. Okay. Yeah, so how translate to quantizations? Yeah, there was in fact something which was dubbed Yang-Mills algebra by Alan adjoint and satisfying this equation which we seen before, this equation of motion. The classical limit will be like this. And why is it called Yang-Mills algebra? Because when I consider a trivial bundle on Rn, trivial complex vector bundle of arbitrary rank, and consider a connection which is constant in obvious sense, so translation invariant, so coefficients of connections in trivialization will be constant. And xi here have nothing to do with this xi in classical limit, just coordinates in Rn. We write this constant connection, and if you write Yang-Mills equation, you don't have derivatives here, you get exactly this thing. It's a part of Yang-Mills equation without derivatives. Maybe when you write connection, you usually do it ai, not xi, these things. So you see that representation of Yang-Mills, finite dimensional representation of this Yang-Mills algebra is the same as kind of class of translation invariant solution of Yang-Mills equation. Now we want to play the same game and say that Yang-Mills equation follows from some Hermitian Yang-Mills equation, which has first order. And the algebra is a pretty simple one, but it wasn't considered by Kohn and Viollet at all. It's I call it Hermitian Yang-Mills algebra. It exists when this n is integer number, it's even number, 2 times m. So R to n will be complexification of it will be complex vector space. And what I write again, write to m the same number of generators, but it's just linear combination of x's. I arrange in m adjoint pairs, like complex coordinates as a combination of real coordinates. And the equations are the following. The first, this equation said that it's the commute for I, this is the I commute, and star conjugate also commute. And this real Hermitian, it corresponds to notion of holomorphic connection. And real Yang-Mills equation for metric is this one, sum of commutations is equal to 0, and the classical limits, it looks completely parallel. So if you have the solution of this equation, then you get solution of this equation. You express x as a real imaginary part of z. And in fact, in this Yang-Mills algebra, one can make some deformation, a few constants, which still imply a classical Yang-Mills equation, namely the I could be not necessarily commuting, and this right-hand side of Yang-Mills equation should be certain constant, real constant. Here you get arbitrary skew-symmetric metrics of complex numbers, and arbitrary real constant gives a deformation of Hermitian Yang-Mills algebra. So translation invariant solution of the things is finite dimensional representation. Hermitian Yang-Mills the same finite dimensional representations like in considered Viollet case.
Maxim, there's a question in the chat.
Yeah.
The question is your Hermitian Yang-Mills algebra just a pre-projective algebra?
Yeah. No, because I have the equations that they commute. No, it's not pre-projective algebra. It's contained algebra of polynomials and m variables. This pre-projective algebra will arrive very soon. Just next slide. Yeah, and then there is something which actually pre-projective algebra, which I called King's algebra, because I'm interested from the point of view of star algebras. And I called free Hermitian Yang-Mills algebra. You just forget commutation relation between T and T separately and T star separately, and you get just only one equation in this algebra. So people definitely seen it many times in different aspects, but why it called Sirkin algebra, I explain in a second. Yeah, so there's what is the relation between these two algebras? We get Young-Mills algebra when we get Hermitian-Mills algebra when for the T commute and T star also to commute, so it will be quotient of free algebra. And so we get homomorphism from Km to Hermitian-Young-Mills, and also those relation between Young-Mills and Hermitian-Young-Mills, because any solution of Hermitian-Young-Mills equation gives solution of Young-Mills equation, means that you get homomorphism of algebra in opposite direction. So there's this nice small diagram of morphism of star algebras. And White-Skin algebras, for me, it's algebra by the following reasons. This is theorem by Alistair King many years ago, actually a particular example of a more general result, which I'll talk in a moment. Let's consider finite dimensional star representation of this algebra up to star isomorphism, just collection of Hermitian operators such sum of commutations equal to 0 up to unitary transformations. And the claim is the same as finite dimensional semi-simple representation of free algebra without any star stuff up to isomorphism. And here this new word here, semi-simple, appears. So it doesn't have it's a direct sum of simple representations. And if considered simple star representation, it will be exactly simple representation of star algebra. And any simple representation will exist unique up to scale Hermitian product such that it solves this equation. So what the explanation of the story? What a representation of free algebra up to isomorphism? It's just collection of matrices modulo action of J and C. And it's easy fact that what is geometric meaning in this language of representation to be semi-simple? It means that the corresponding orbit is closed. Now I make a very brief review of geometric invariance theory and relation to moment maps by Mumford and Kempf-Nets by symplectic side. If you have any reductive group, or let's say complex numbers and finite dimensional representation, choose a compact subgroup, and for compact subgroup get invariant Hermitian norm, so embed it to unitary group. Now, suppose I have a vector such that orbit is closed. Then, because it's closed, then the function's square of length, which is bounded below, achieves the minimum. And the theorem it's actually goes in both ways. And in fact, for any such orbit when this minimum is achieved, the minimum is achieved on exactly one orbit of the maximal compact subgroup. Yeah, and this is related to symplectic geometry because when we have Hermitian form on complex vector space, we get symplectic structure, so we get just flat symplectic vector space. The action of maximal compact group will be Hamiltonian, given by quadratic Hamiltonians, and so we get a moment map from vector space to Lie algebra. And when consider set of closed points on orbits, which on all possible orbits, which happens to be closed, then I get exactly a preimage of 0, which will be a closed subset, but not complex one. So, and when I consider the section of JLN on collection of matrices by simultaneous conjugation, the moment map is given by this thing. So you see that orbit is closed when it achieves a minimum, and then achieve minimum has 0 for moment map. So you get sum of commutations equal to 0. So this gives you a proof of King's theorem. But here there's something really funny goes on. And because consider now any associative algebra which is finitely generated. choose any finite collection of generators and consider what a finite dimensional semi-simple representation of algebra up to isomorphism. You represent your algebra as a quotient of free algebra, yeah? So to represent free algebra, when generators satisfy certain relation. But closures of the orbit, it's for the things doesn't really matter. It's satisfactory relation, doesn't satisfactory relation, so it's all the same. And so you see that it's because it will be semi-simple representation of free algebra as well. You see that you get representation of certain star algebra, which obtains the following. Oh, it's actually again misprint. It should be free product, not tensor product. So I see my misprints here. It's a free product of algebra and formal star dual. Modular relation, the sum of commutator is equal to 0. Yeah, so for any associative algebra, any finite sense of generator, we can describe this semi-simple representation in star theoretical language. But in this description, there's really generators plays absolutely no role. So you can choose different collection of generators for the same algebra, you get different star algebras, and these two different star algebras have the same series of finite dimensional star representations because they correspond to the same equation in for A. And conjecture that how it happens that two different star algebras have the same finite dimensional representation should be because star algebra is not complete. So I really don't know the story, but should make some completion. And it doesn't depend on the choice of generators. For example, this kind of very precise question which I have, if you have this star algebra B, which depends on the choice of generators, one can consider space of normalized states. So it will be linear maps which compatible with real structure, and on positive elements of algebra are non-negative, and it will be 1 or 1. You can put also trace states which vanish on commutators. So it will be certain part of it. And the conjecture, this thinks it will be certain infinite dimensional convex body, doesn't depend on choice of generators. And this convex body could be non-empty even algebra has no finite dimensional trivial, non-trivial finite dimensional representation. So there will be some kind of like representation factors which will give such traces. Okay. Let's return to finite dimensional presentations. If we choose our generators, then we embed the story in kind of moment map geometry, and we have natural Kaehler metric on a quotient space and Kaehler potential. And Kaehler potential is given with the following. We consider a function on space representations, and we represent by this canonical Hermitian representative, so like King's equation, we have certain positive real valued function. And this function on a singular reduced affine scheme, we consider semi-simple representation of my algebra. If it has relation, it will be kind of very singular variety, maybe not equidimensional. It's free, it's easier. So it will be, but whatever, if you get any finitely generated algebra, you get a singular reduced affine scheme of finite type. And this function, it will get strictly pluristyric harmonic function. This thinks it will be potential on singular Kaehler metric. For example, consider smooth locus of this guy, or any smooth subvariety, it will be potential of Kaehler metric on the smooth subvariety. Yeah, so this metric is given by dd bar of Hn. And so you see that on this, you get a growing family of affine schemes of finite type. On each scheme, I get a Kaehler metric. And given kind of by universal formula, it just depends on the size. And that I see that can interpret that you had something like non-commutative Kaehler metric on this non-commutative algebra. And this Kaehler metric will be kind of very special size form because the potential is given by finite sum of squares of holomorphic function, roughly speaking. I'll try to see that it's the following way. It's my algebra is a quotient of free algebra. M is the number of generators. Then the spectrum of algebra is embedded to spectrum of free algebra, whatever it means. It's some kind of non-commutative vector space. And this on this non-commutative metric space, because I have choice of generator, I get flat metric. given by this expression, and that induces flat metric on the spectrum. So that's kind of intuitive picture. What is this? Should be this Hermitian Kaehler metric, but one can maybe try to get some definition, which I'm not ready yet. So if this conjecture about independence of star completion on the choice of generators means that we get some kind of nice complete star algebra depending on the generators, and when you choose different choice of star completion, choice of generator, you embed your algebra in different ways, but this ways differ by conjugation by invertible element. Yeah, so it looks that you get the picture is the following: get some universal star algebra and get many embeddings of A differ by invertible elements of B, and it looks from this formula that this non-commutative matrix is the choice of one of these representatives of this embedding.
Sorry, I have a naive question. What if I have presentations with different number of generators?
It's okay. It's okay. Yeah. So get different embeddings from A to universal. Universal guy will be still the same. That's a conjecture.
But you say this invariable element B. How would it if the number of generators is different?
No. The claim is this B universal doesn't depend on your generators.
Mm-hmm.
Yeah, and but then you embed your algebra because algebra doesn't have star structure at all. A.
Mm-hmm.
Yeah, so I claim that if you choose the generators, you because it's algebras, when you choose generators, contains your algebra A as a part. Yeah.
Mm-hmm.
Yeah, but if you choose different generators, it contains I in different way. And in fact, the idea how to prove that things independent on generators, you start, for example, kind of rescale a little bit one of generators, for example. Start to rescale one of generator, and then you should kind of conjugate embedding by certain element infinitesimally. That's the idea how to prove it. And then you can add copy of generator, rescale to 0, and then play the game changing number of generators.
Okay, thank you.
Yeah. Okay, so I think I press. Sorry, my computer is frozen. It's bad.
So alternatively, Maxim,
Yeah.
I can share your slides and then.
No. Yeah, okay, you can share my slides. Yeah, but I'll just name the number of page because page are fortunately numbered, and I'll read them. Yeah, show some other things. Just a second. Okay, so now go to page 15. Yeah. Okay.
Yeah, we do see page 15.
Okay, yeah, so it's fine. It's fine. Yeah. Yeah. So what goes on? I explained you King's theorem, but in fact he proved some more general result for representation not of free algebras but for quivers. You consider arbitrary finite quiver. So it has vertices, edges, and for each edge you have tail and head. So a set maps to square of another set. And representation, it's obvious things everyone knows. For each vertex you get vector space, and for each arrow you get a morphism, map from one vector space to another. Now suppose I get, for each vertex I get a weight, some real number, and a representation is called mu stable, finite dimensional representation called mu stable if linear combination of dimension with this weight is 0, and for any proper sub-representation this thing is strictly negative. And representation is called polystable if it's some direct sum of mu stable ones. So in fact, one can define some notion of polystable representation, but I will not go to this thing. And the theorem by Alistair King is the following: the isomorphism class of mu polystable representations are the same as isomorphism classes of star representation of algebra, which is the following one. Yeah. So what's really goes on? You have a representation of your quiver, and you put some Hermitian form on each vector space and consider direct sum. of all vertices. On this direct sum, you get projectors, orthogonal projection to the direct to summons, which is not pi v, which is self-adjoint operator. Sum is equal to 1, and the product pi square is equal to pi, and different product is 0. So it's decomposition of one sum of projectors. And then you get arrows, and then I express that arrows goes to one space to another, adjoint arrows go to adjoint space. And just put this equation with the right hand side. So in the total direct sum of all EV for all vertices. Both operators will be things acting in each individual vertex. And in this situation, one can generalize conjecture for uniqueness of star completion. So one choose kind of rescale generators in your quiver and should get the same star algebra because it's the same question. Okay, go to page 16, please. Yeah. So like finitely generated associative algebras are the same as quotients of free algebra by some relations. The same for quivers if consider finitely generated algebra which contains algebra of functions of finite set, then it will pass algebra of finite quivers modulo, again, arbitrary relations. And yeah, so it's a little generalization, but now I want to go to some generalization of pass algebra of quivers, which goes to some kind of continuous version. Instead of function of finite set, we get functions on manifold. And it will be pretty abstract picture. So D, my algebra will be, instead of quotient of pass algebra of quiver, will pass algebra of certain guy called D. D is the following gadget. I start with associative algebra D less than equal to 0 or D0, just some associative algebra, unital one. Have any bimodule of it. And I have a morphism of bimodules, diagonal bimodule to this guy. This morphism small I. And then I can form kind of free algebra generated by bimodule, consider D0, D1, and take product of D1 over D0 arbitrary many times. It will be free algebra generated by bimodules, modeled out by relations that part of D1 which come from D0, it's really come from D0. So it's these relations. And so I get a filtered algebra. And the first example, if you start with quiver, I take D0, it will be projector to vertices, and again, missplit, D less than 1 will be projector vertices plus arrows. And then I get pass algebra filtered by lengths of the path. And another story is actually quite interesting one. I consider algebra of functions, complex values, say functions on smooth manifold. And D1 will be differential operators for the 1. It's definitely bimodule, multiply when left, right, get differential for the 0, and contains functions. So you can apply this procedure and get certain filtered algebra, which is called free differential operators. In local coordinates, you write expressions in x in d over dx, but d over dx are not commutative at all with each other. So it says Leibniz rule. So you can write x on the left, commutative with each other, then d over dx form a free algebra. It's close to what Kapranov considered a long time ago. And so you get this free differential operators. And if you consider modules of this thing which are free as modules or algebra functions, finitely generated, it will be the same as vector bundle, because finitely generated things, if it's projective, it's vector bundle, and not necessarily flat connection. When you're interested in flat connection, go to the quotient and you get usual differential operators. Okay, so there's analogous analogy between pass algebra on quiver and this free differential operators. One can also apply to difference equations. It will be the same formalism. Now go to next page, 17, please. Now I will write you this general kind of way how to generalize not King's theorem, but at least equations for King's theorem. So what I want to define some kind of moment map, Kaehler metric on space of Eisenberg class of polystable representation. I don't know what is fully stable, but at least formals what I can write. So I start with this formalism. I get d less than 0. Now it will be star algebra, like functions on vertical quiver or functions on manifold. And instead of defining this bimodal d less than 1, I go to dual language. Instead of vector fields, I consider forms. So I consider some bimodal omega 1, it will be just bimodal. It will be finitely joint projective as a right module, and let's assume that I have a derivation. So it's Leibniz rule from d less than 0 to omega 1. Then if I get a derivation, I get an extension of bimodules. And when I get extension, if I go to dual bimodules making whatever right dual, making is right home less than 0 is a right bimodule, it will be d less than 1 and automatically get this embedding of a diagonal. Yeah, so it's essentially equivalent the story to have a bimodule and have this embedding. By dualization and choose splitting is the same as get things with derivation. So it's kind of more convenient language to describe this bimodal and a map. Yeah, so it will be, now I want to say something which will be analogous to inverse to Kaehler form on what to be non-commutative space. I consider pre-Hilbert form or pairing on omega 1, which is compatible with bimodal structure in the way which I wrote in this axiom 3. In star algebra, it's very well notion if you have bimodal, it can have kind of Kaehler form with this compatibilities property. And analog of weights will be a linear map satisfying some reality condition and some condition for commutators. What does it mean? In this formula which I wrote for on the right hand side, you get certain expression f and g, which is cyclic to a chain. It just follows from properties that it's derivation, and I get this compatibility of Kaehler form with product. So I get cyclic to a chain, and this story says that this chain is a K-boundary. Now, so that's for me the setup when I can try to write kind of moment map equations. What is the idea? We can really start to think about quivers, or that you get notion of bundle, connection, not necessarily flat, and get gauge action and blah, blah, blah. And then you get this moment map story. Yeah, so it's some abstract formalism, and one get yeah. So what's really goes on? I consider finitely joint projective module over algebra D0. It's like vector bundle or finite collection of finite vector space in the quiver case. Then I get notion of connection by usual calculus with omega 1 or action of d less than 1, as you like. It doesn't matter. And then for this connection, one can define what is a norm on the bundle, and then on right moment map, it will be some moment map, some infinite dimensional gauge group. We get some moment map, and go to page 18, please. So yeah, so you get some kind of generalization of King's equation, but not only King's equation, because we have more examples. Because algebra could be algebra function on a manifold, not algebra of function of finite set. And in continuous case, you get a whole bunch of equations from mathematical physics. So you get, oh, sorry, I go a little bit over time. Sorry. You get Hermitian equation, Nam equation, Bogomolny equation, Hitchin equation, Waffe-Witten equation, something called vortex equations, which considered by Alvarez, Consul, and Garcia Prada. But all these things are only for unitary group. And also then can go to algebra of even different type, really non-commutative algebra, not functional manifold. You consider functional quantum vector space. even vector space, or maybe quantum torus, and then get non-commutative instantons for Douglas, Nekrasov, and Schwarz. So next page, please, 19. Yeah, so it's just one simple formalism which goes to many places. And what is quantum CM? Quantum complex vector space. It's a real vector space and of dimension 2m, on which you choose m complex coordinates, z and z star, and they satisfy these commutation relations. You can go to real imaginary part to get the quantization of R to m. And you consider, of course, not only polynomials, but some kind of C-infinity function with appropriate type. And this algebra has a lot of commuting derivations. You can shift variables still here. And what is non-commutative Hermitian instanton? It's finitely generated projective module. Again, some small misprints of this guy. It's like vector bundle, C-infinity vector bundle of the space, endowed with a Hermitian norm, which is something that's mapped from now to the algebra, satisfies these identities, and covariant derivatives with vector commuting derivations, which satisfies the following commutation relation with respect to with itself and also with coordinates, and also compatibility with the norm, and in this one equation in green, which is Hermitian equation. Yeah, so you get this huge data. Let's go to page 20, next page, 20. So this there was a kind of a bit informal construction in about 2000 by Furushi and Nekrasov, almost the same time. They both cite each other. So this non-commutative Hermitian instanton gives an infinite dimensional solution of King's equation. And this construction goes the following way. On this algebra functions on, again, wrong equality, on a quantum space. One can see the state mapped to real numbers. It's positive on this Hermitian squares. And the state depends on certain scale, R. And it's written by explicit form, which is was here. Then this case, when you get a bundle with this, it's something like measure positive density on underlying vector space. It will be exponent minus rho times z square, roughly. Then when I get a scalar product on the bundle, I can integrate with respect to this measure, and I get actual pre-Hilbert space structure, and applies T rho to this algebra valued Hermitian product, and I get this very big space, more or less L2 section of E with respect to certain L2 norm. Now consider these operators here, because I get coordinates and covariant derivatives. I get some linear combination depending on this rho, and it's a very nice linear combination because easy calculation shows that what's this Hermitian adjoint with respect to this Hermitian panic will be rho times covariant derivatives. And if you like the sum of commutators, exactly for each commutator you get rho times identity, you get King's equation. But this King's equation is really huge space in L2 sections. And this is really non-trivial fact. It's not really rigorous, this argument, that if you consider this kernel of this d-bar derivatives, it will be roughly like holomorphic sections of your bundle, which will be much smaller space. This operator zi and zi cross preserves the subspace. For zi, it's obvious. It follows from the definition. But for zi cross, it's some kind of a bit informal argument, which it's not rigorous yet, but very convincing. So you get on this subspace, you again obey King's equation, it's still the desired solution. So it's analogous space of Hilbert sections, some kind of like finitely generated module, and it could be projective module, like vector algebraic vector bundle, but it also could be not projective module. It could be torsion-free sheaf, ideal of a finite subscheme. It's not reflexive sheaf, which people like in usual Yang-Mills equations. So it's something really new. You get notion of Hermitian metric on this torsion-free sheaf, which is not a vector bundle at all. What is nice here, this is not a vector bundle, but this big space is a vector bundle. Yeah, so it's something funny goes on here. And please go to the next page. Yeah, so how it's related to, yeah, I just make a kind of long detour. So how it's related to minimal surfaces. Minimal surfaces are gadgets of very different nature. Imagine suppose you get some polynomial two variables and you take not ideal sheaf of polynomials, which is not really interesting, but quotient-based ideal. You get function on a curve. And this is torsion model. So one cannot speak about non-commutative Hermitian Instantons at all about these things because it's not a vector bundle. There's no notion of connection. But so one cannot, this Hermitian story is kind of disappears here, but infinite dimensional equation still makes perfect sense. I want to make some pre-Hilbert norm on this infinite dimensional space and make a completion and write this equation, sum of commutations is equal to identity. And in fact, physicists considered it also a long time ago, even before this Hermitian story appears, and before 2000, like by Washington Taylor Force and his student Carnalba. They have a couple of papers. There's no really follow-up after this paper. It was no mathematician never read it, and physicists maybe read but forgot. It was some string theory, M theory motivated. So they look on this equation, study a few examples. And these equations, which I said it's kind of solution of this equation, sum of commutations is equal to 0, it implies this minimal surface. It will be quantum minimal surfaces which are supersymmetric, so it's non-compact complex curves. And there was one simple example which actually Carnalba and Taylor didn't discuss. They forgot to look on it. It's really the simplest possible examples when you can do everything. It's in closed form. The example is not in closed form. You can see the hyperbola given by product of two coordinates equal to 1, you parameterize by coordinate z. So algebra function has basis consisting of monomials where n is arbitrary integer, positive or negative. And if you write the equation, sum of the scalar product, they are orthogonal to each other and have unknown things which are scalars of length, then this equation gives you this nice recursion. Yeah, so you get pretty strange expressions, but it solves this equation. And yeah, so it's kind of different gadgets. So it's not a torsion-free model, it's a really torsion model. And the conjecture should be formulated precisely that for any stable, in certain sense, finitely generated module which support on certain dimension d, it could be from 0 to m. M is correspond to what in Hermitian stories, 0 correspond to finite dimensional presentation, and intermediate case will be curves, or maybe some intermediate dimensions. And even put certain condition to infinity, then you'll get unique up to scalar pre-Hilbert norm. Such that sum of commutations will be rho times d, and rho will enter in the boundary condition, and d will be dimensional support. So for dimension 0 dimension support, you get 0. Here for curve, you get 1. And boundary conditions, I think it's a solution of classical Yang-Mills equation on some variety at infinity. We consider intersection of support with CP infinity, puts Fubini's 2D metric here, and solve Hermitian equation in classical sense there, and it will be limit of the story to infinity. Thank you. So next page, thank you. Okay.
Well, thanks a lot.
Yeah. Sorry for get a little bit over time.
Well, are there some questions or comments?
In the first part of your talk, is there a kind of Feynman integral quantization of the shield action? What kind of thing?
One can try to integrate. You see, it actually looks right. It's n times trace, yeah?
Yeah, exactly.
Yeah, so it looks like it wants to be quantized like in matrix integrals, but I don't think anybody considered it. Yeah.
I have a question.
Yeah.
Could you go back to the quantum c to the n? Could you explain how does the quantum c to the n example embed in physics? What is the model that gives it?
No, the origin of the story is the following. You can see the quantum R to n, R to m, yeah? Yeah, first you consider, so you have a vector space with some Euclidean metric, Euclidean metric, and some skew-symmetric form, not necessarily compatible to be Kaehler one. Then there was a series of, in fact, it was this original paper by Kohn, Douglas, Schwarz, and Nekrasov. They defined some kind of Young-Mills equation in this situation. It will be like the second-order equation. So consider module over free algebra, free finitely generated module over quantized algebra of C infinity function, and then derivations. This shift you leave to some derivations of your module. It will be for them a little connection, and they write action, imitate action of Young-Mills, usually Young-Mills action, and get something. Actually, it again was coming from string theory for open strings, I suppose. And then there was a kind of general story, and then they discuss its supersymmetric solutions in a four-dimensional case. It was example of C2 in the paper. And then Nikita Nekrasov many years ago told me about general M and about this equation, and that's how it comes to the life.
So instead of taking kind of like a non-commutative space and then doing gauge theory, imitation gauge theory on the non-commutative space.
No, the space is non-commutative, but it's contained commutative. These holomorphic variables are commuting.
Yes.
Z bar is not commuting. Exception is real space is not commuting, but contains commutative space and consider things which is D bar invariant. You get actually commutative algebra. Right. One can also consider Z to be non-commuting as well. And then it will be really something very funny when consider like D modules. It will be not holonomic D modules for them. It will be D modules which are almost like 3D modules. And for this 3D modules, you get still notion of Hermitian, this harmonic something. And with this reformulation with King's equation, you get actually notion of harmonic metric on not 3D module, but like holonomic D module. Yeah, so it's a lot of possibilities here.
But my question was really about the interpretation of the Z's, these quantum operators. Does it come from matrix models or some? Is there some?
It comes from matrix models. You can really read this first paper. They have really nice discussion about dualities, and so on. Yes. For example, if they go also to Tori, and then from you get Tori, and says solution of Young-Mills equation one Tori goes to solution against equation dual Tori, and there's a whole story about it. Yeah.
May I ask one related question? So, because in physical applications, there were some generalizations of this IKKT model, including West-Wiener terms.
Yeah.
Some topological terms. Do you have something like that?
No, I'm just writing flat space only. Yeah. But in principle, one can try to do. I think this is very general formalism which I wrote about algebra, star algebra, this bimodal, blah blah blah. Probably will contain various stuff, but I'm not sure.
Could you make a comment about any kind of analog of gluing these things together?
It's very non-local.
Yeah,
I don't know.
Okay, more questions?
Yes, this is Ezra Getzler.
I recognize you. Okay,
yeah. I saw you had the idea of differential operators, but with the differentials not being a flat connection. But curvature is somehow smaller than just a second-order differential operator. I wonder if that was in some sense hidden in your algebra.
Not really. Yeah, no, it's a different. It was a different story when you consider this free algebra. Like consider this free connections. Yeah.
Mm-hmm.
When you write this, whatever this. The story is the following. You consider, let's say, any compact manifold, any bundle with not flat connection.
Yeah.
And suppose it's some kind of irreducible, doesn't have subbundle. Yeah. The claim is it will have unique and putting on a manifold any Riemann, some Riemann structure, yeah, claims that it will be unique metric on your bundle, satisfying some kind of Yang-Mills equation. Yeah, just for any non-flat connection, small or not small doesn't matter. Yeah, and the story is that this formalism which I wrote and what cyclic Tuka cycles, it's very, very soft. It includes much more examples than one see immediately. One can have any Riemannian manifold, for example, or you can have a manifold with foliation, transversal complex structure, or maybe not integral complex structure. So there are really a lot of, and you don't need even to be Kaehler form to be closed. Only n minus 1 degree part should be closed. It's much weaker conditions you get.
Right.
For the whole moment map story to exist.
Okay, I'll think about this.
Yeah.
Thank you.
Okay. Any more questions or comments?
Besides the Weierstrass representation for minimal surfaces, is there another type of problem that you think should be transformed into this framework?
I don't know. No, but Weierstrass, I think it's a nice open question. Yeah, how to think. Yeah, I really don't know. Yeah, essentially, you wrote this shield action. We get topological terms, which I translated. Yeah, I don't know what else. Yeah. Yeah, no. In principle, I'm not really happy with my action functional for the map to torus. If you remember, there was something like cosines, a trace of identity operators minus commutator. Yeah, it was somewhere. What was this page? It was page. Maybe very early in the stock. It was page 7. Go to page 7.
Sorry, just a second.
Yeah, you see, you get this. Ah, no, wrong. I think it's page 6. Page 6, you see that the section 2 times identity operators. Actually, what I really would like to have, maybe modify it a little bit, just to have it the same behavior, but to get on the nose BPS inequality. When on page 7 I get notion of degree, yeah. So the degree will be low bound for area squared, and then equality should be satisfied when I get holomorphic curve in a quantum in a torus, for which is a well-defined notion. And in our paper with Arland and Hoppe, I think there's a small paragraph discussing quantum curves in abelian varieties.
Would it make sense to consider the A model and the B model on such a thing, on such a quantum Kaehler?
Actually, it's a good question. Yeah, that. Yeah, because we have notion of map of a surface. Yeah, here one can try to make certain sums. Yeah, I don't know.
All right. More questions or comments for Maxim?
Oh, sorry, I think I hide myself. Okay, maybe I'll hide.
So right now, what are the compact Kaehler examples?
No, there is compact Kaehler examples. For definitely the flat tori is a nice class of compact Kaehler example. I will start with this. Yeah, in fact, there's also an interesting story which I started to think. If you consider compact Kaehler examples, or maybe just do minimal surfaces in tori. if you consider minimal surface as a torus, it's explained it's some kind of like equation of algebraic geometry. Yeah, you get this very sparse representation, and then it depends on the choice of constant real metric on a torus. And then you should get certain wall crossing here, I suppose. This number of minimal surfaces jump by certain rules. Yeah, it will be really interesting to explore how it jumps. In complex case, also there are some kind of Gromov-Witten invariants for abelian variety, three-dimensional abelian varieties. So that's, yeah, so one can go in this direction as well. So one can count either minimal surface or the supersymmetric minimal surfaces. Minimal surfaces are really nice because they exist in for torus of arbitrary dimension independent on the genus. So it's something really, really cool.
Well, yeah, if there are no more questions, let's thank Maxim again for this wonderful presentation.
So I think I now have to repair my there are many misprints. Okay, but okay.
Well, that's just to remind to everybody that next week there will be talk of Boris Kessin. So see you again on Global Poisson, and well, thank you all for participating.
Okay, thank you.
Thanks for organizing.